Hi and welcome back. In this section, we'll take a look at vision transformers, which are, pardon the pun, transforming the computer vision world right now. And they're almost replacing CNNs in many of the state-of-the-art computer vision deep learning tasks. So let's get started. So what exactly are vision transformers? Well, what they're not those transformers from the movie. And they're also not electrical transformers that do step up or step down voltage changes. What they are, it's actually something, it's a method or algorithm, you can say, or a type of neural network design that came from the NLP world in a famous paper in 2017 that was called Attention is All You Need. And this was a groundbreaking paper in the NLP world because it allowed them to encode way more information into their networks and beating LSTMs and RNNs at the time at so much NLP tasks. And pretty much now it's all they do is transformers and NLP. If you want to do state-of-the-art stuff, at least not simple classifiers, but state-of-the-art NLP is almost all transformers. And that is almost changing in the computer vision world right now. And they use something called self-attention, which allows us to take sequential inputs, like words, and find the correlations between different features and stores that information as part of the network's knowledge. And from 2020, it started to gain a lot of traction in the computer vision world. And you can see why. You can see in this task here, or in this model, this T2T vision transformer, it's actually beating ResNets and previous VITs as well, and in accuracy and model size and max as well. And you can see in model size it's actually getting better results from a similar model size to MobileNet Vision 2. And this is just one transformer network that the researchers are presenting here, comparing it to a few other popular networks. It doesn't mean this is the best right now, but it's pretty good. So how is it used for images? Well, firstly, we've got to split an image into patches and then flatten those patches and then create, basically out of those patches, a lower dimensional linear embeddings formed from those flattened patches. And then next we add a positional embedding alongside of this lower dimensional vector that we've created. And usually this is a trainable position embedding that's typically used. And then we feed that sequence as an input into a standard transformer encoder. And next, we pre-train the model with image labels from a very large data set, something like ImageNet. And then when you want to train it on your own data set, you fine-tune that network on the downstream data set for your image classification tasks. Now let's take a look at this very cool animation produced by Google that explains vision transformers. So you take an image here, you split it up into patches as you can see here. Then you have your linear projection of flattened patches. You add the positional embeddings there. And then you pass it to the transformer encoder, carries it to an MLP head, and then we predict the classes out of it. So let's watch this one more time again. You can see they add the positional embeddings here after we have the projection of flattened patches. This goes into a transformer encoder, then to the MLP head, and then classify results go here. So let's talk a bit more about vision transformers. So the image patches are analogous or equivalent to sequence tokens, which is words in NLP. That's how we treat images as inputs into a transformer network, which relies on a sequential input. And if you wanted to get a deeper vision transformer, you can just increase the number of blocks inside of the transformer encoder. And these are what the blocks look like. This is a multi-head attention. That's one of the important parts, or the most important parts of the transformer encoder. And it's important to know that VITs do require a lot of data to be trained to even beat or compare to state-of-the-art CNNs. So that basically means training from scratch when your smaller data set is not really an option with vision transformers. So you may as well stick to CNNs. Something like a small CNN, like a ResNet 18, would probably work well for most general image classification tasks. However, what we can do is take a pre-trained vision transformer and then fine-tune it on your smaller data set and change the MLP head outputs to your class size. So if it's like 5 classes or 2 classes, change it, and that's it. So we'll stop there for now because this is just a brief overview an introduction to vision transformers. What we'll do next, we'll take a look at some implementations of vision transformers in both PyTorch and Keras. So stay tuned for that, and I'll see you in those lessons. Thank you for watching.